Welcome to Lesson 6.4 Continued Pre-Training and Domain Adaptation. Overview. This lesson is about transformation. You're going to take a general purpose language model, one that knows a little about everything, and turn it into a genuine domain expert. Through a technique called Continued Pre-Training or CPT, you can specialize a model for medicine, law, code, or any scientific field without destroying the general knowledge it already has. That last part is the hard part, and it's exactly what this lesson teaches you to do. Budget about 90 minutes and expect to earn it. This is advanced territory. Learning objectives? By the end of this lesson, you'll understand the fundamental difference between continued pre-training and fine-tuning, know how to build domain-specific training data from scratch, apply concrete strategies to prevent catastrophic forgetting, execute a full CPT training run, and evaluate whether your model actually got smarter in your target domain. The benchmark we're aiming for: a 20 to 40% improvement in domain-specific performance. Pre-training versus fine-tuning versus continued pre-training. Here's the foundation everything else builds on. Standard pre-training is what companies like Meta did to create Llama in the first place, feeding the model trillions of tokens of internet text with a single objective: predict the next token. That process is what gives the model its general world knowledge. It costs millions of dollars and takes months on thousands of GPUs. You are not doing that. Fine-tuning is the other end of the spectrum. You take that pre-trained model and teach it how to behave, how to follow instructions, answer questions in a certain style, or respond as an assistant. The dataset is small, maybe 100 to 1000 instruction response pairs, and training is fast. This is what most practitioners mean when they say fine-tuning. Continued pre-training sits exactly in the middle, and that's where this lesson lives. Continued pre-training takes an already trained model and keeps training it, but now on domain-specific text, millions to billions of tokens from medical journals, legal documents, code bases, or scientific papers. The task is still next token prediction, same as original pre-training. The difference is the data. You're not teaching the model new behaviors, you're injecting new knowledge. After CPT, the model genuinely understands your domain's vocabulary, concepts, and reasoning patterns in a way it didn't before. The clearest way to think about this: CPT teaches knowledge, fine-tuning teaches behavior. If you want a general assistant, fine-tuning alone is enough. If you want a medical diagnosis AI, you need CPT first to load the knowledge, then fine-tuning to shape how it communicates that knowledge. If you're adding support for a rare language the model barely saw during pre-training, CPT is non-negotiable. The two-stage pipeline, CPT then fine-tune, is the professional approach for any serious domain specialization, creating domain pre-training data. The data requirements for CPT are fundamentally different from fine-tuning. Fine-tuning works with tens of thousands of carefully crafted instruction pairs. CPT needs raw text, lots of it. We are talking 10 million to 10 billion tokens in plain prose format, sourced from your target domain. Quality matters more than quantity. Domain-relevant text that actually reflects how experts in that field write and reason. With your 2 Tesla P40s, a realistic and practical target is 10 to 100 million tokens, which should complete in 2 to 10 hours depending on your dataset. This script builds a medical CPT dataset by pulling abstracts directly from PubMed's API. It searches for cardiology and oncology papers published between 2020 and 2024, retrieves the PubMed IDs, then fetches the actual abstracts in batches of 100. That batch size exists to stay within the API's rate limits. There's a half-second delay between requests for the same reason. Each abstract gets extracted from the XML response and appended to the dataset. After collecting both specialties, the script merges them. prints the total document count and an approximate token estimate, then saves everything to disk. The token estimate is your first sanity check. You want to see millions, not thousands. For code domain adaptation, this script taps into the stack dataset, one of the largest open collections of source code on Hugging Face. Notice the streaming equal sign true flag, that's critical. The stack is enormous, and streaming means you pull examples one at a time without downloading the whole thing. The loop collects the first 50,000 Python files, printing progress every 10,000 to confirm it's still running. Each example is stored with its text content, source, and language metadata. The final output is a JSON lines file, one document per line, which is the standard format for large text datasets because it's memory efficient and easy to stream during training. For legal domain adaptation, the script loads from Pile of Law, a curated Hugging Face dataset of court cases, statutes, and legal documents. The key line to notice is the filter. Any document shorter than 500 characters gets dropped. That's deliberate. Short fragments don't give the model enough context to learn legal reasoning patterns. You want substantial documents, full case summaries, complete statutes. After filtering, the clean dataset is saved in JSON lines format. The printed count tells you how many documents survived the filter. If that number drops dramatically, your source data may have quality issues worth investigating. Preventing catastrophic forgetting. Catastrophic forgetting is the most dangerous failure mode in continued pre-training. Here's what it looks like in practice. Before CPT, your model correctly answers that Paris is the capital of France. After CPT on medical data, it can explain myocardial infarction in detail, but it's forgotten Paris. The model overwrote general knowledge with domain knowledge. That's not a domain expert, that's a broken model. The goal is additive learning. The model should know both. Everything in the next section is designed to prevent this exact problem. The primary defense against catastrophic forgetting is data mixing. This script loads your domain-specific data, in this case medical texts, alongside a general-purpose dataset from Wikitext. It then samples the general data to match the size of your domain data, shuffles both, concatenates them, and shuffles the combined result. That final shuffle is important. You don't want the model to see all the medical text first and then all the general text. Interleaving them forces the model to continuously practice both types of knowledge throughout training. The script prints the sizes of each component and the final domain to general ratio, so you can verify the mix before committing to a full training run. The right mixing ratio depends on how specialized you need the model to be. Heavy specialization, 70% domain, 30% general, maximizes domain performance but carries more forgetting risk. A balanced 50-50th split is the safe default for most projects. Light specialization at 30% domain, 70% general is appropriate when you want a gentle nudge toward a domain without sacrificing general capability. Start balanced and adjust based on your evaluation results. Learning rate is your second major lever against catastrophic forgetting. When Meta pre-trained Llama, they used a learning rate of 3E4, aggressive because they were training from scratch on a massive dataset. When you fine-tune, you drop to around 2E4. For continued pre-training, you go lower still, between 5E5 and 1E4. The intuition here is straightforward. A high learning rate makes large weight updates, which risks overwriting existing knowledge. A low learning rate makes small, careful adjustments, nudging the model toward domain expertise without bulldozing what it already knows. That's the core principle. Preserve existing knowledge, gently add new knowledge. The learning rate is how you control that balance numerically. For CPT, one epoch is usually the right stopping point, and in some cases, even half an epoch is sufficient. This is counterintuitive if you're used to fine-tuning where multiple epochs are common. The difference is data scale. Your CPT dataset contains millions of tokens, so even a single pass exposes the model to an enormous amount of domain knowledge. Training beyond one epoch on the same data increases the risk of overfitting to your domain corpus and accelerating forgetting. One epoch, watch your metrics, and stop early if general knowledge starts degrading. The practical way to catch forgetting early. Run a short general knowledge quiz, basic geography, history, science, every few thousand training steps. If those scores start dropping, you have a forgetting problem and need to intervene before it gets worse. Continued pre-training script. This is the full CPT script, and it brings together everything covered so far. It loads llama-3.2-3b-instruct in 4-bit precision using Unslaw's fast language model, then applies LoR adapters to make training memory efficient on your P40S. The domain data is loaded from disk and tokenized for causal language modeling, next token prediction, no masking. The data collator is configured for causal LM specifically, which means the model learns to predict every token in sequence rather than filling in masked positions. Training arguments are set with the low learning rate and gradient accumulation appropriate for CPT. After training completes, both the adapted model and tokenizer are saved to disk. That saved model becomes the input to your fine-tuning stage. Evaluating domain adaptation. The test_domain_knowledge function gives you a concrete way to measure whether CPT actually worked. It puts the model in inference mode, tokenizes each test question, moves the inputs to GPU, and generates a response with temperature set to 0.3, low enough to get focused, deterministic answers rather than creative ones. The original question is stripped from the output, so you're reading only the model's generated answer. Run this function on the same set of domain questions both before and after CPT. The comparison is your ground truth. Did the answers get more detailed, more accurate, more fluent in domain terminology? That delta is your evidence of successful adaptation. The expected improvement is qualitative as much as quantitative, more precise terminology, deeper mechanistic explanations, fewer hedges on domain-specific facts. This script handles the other half of evaluation, checking that general knowledge survived. It defines a set of baseline general knowledge questions, runs them through your adapted model using the same test_domain_knowledge function, and prompts you to manually verify each answer. The final calculation gives you an accuracy percentage. If that number falls below 70%, the script flags a catastrophic forgetting warning and recommends two concrete interventions: increase the proportion of general data in your training mix or reduce the learning rate further. Both of these pull the model back toward preserving existing knowledge. Don't skip this evaluation. A model that aced domain questions but forgot basic facts is not production ready. This evaluation checklist formalizes what success looks like. Domain knowledge is scored across 5 dimensions: terminology accuracy, depth of explanation, ability to reason within the domain, handling of edge cases, and factual correctness. General knowledge is checked separately: basic facts, common reasoning, language fluency. Each dimension is rated 1 to 5. The success threshold is a 4 out of 5 on both sides, domain and general. That dual requirement is the point. You're not optimizing for one at the expense of the other. A score of 5 on domain knowledge with a 2 on general knowledge is a failure. You need both. Complete CPT to fine-tuning pipeline. This code sets up the CPT trainer with all the parameters you've configured. The output_dir tells it where to save checkpoints and the final model. The learning_rate and num_train_epochs reflect the conservative values we chose: low rate, 1 epoch. The train underscore dataset points to your mixed domain plus general corpus, which is the critical ingredient for forgetting prevention. After calling train, the model is saved to disk. Expect this step to take 2 to 6 hours depending on your dataset size and hardware. That saved directory is not your final model. It's the domain-adapted base that feeds directly into the fine-tuning stage. The fine-tuning stage picks up exactly where CPT left off. This script loads the domain-adapted model you just saved, then sets up SFT trainer, unslots supervised fine-tuning trainer with a dataset of medical question and answer pairs. Notice the learning rate here is 2E4, higher than what you used in CPT. That's intentional. Fine-tuning is shaping behavior, not injecting knowledge, and the model's existing weights are already well suited to the domain. The higher rate allows faster behavioral adaptation. After training, the model is saved as your final medical assistant, a model that now carries both deep domain knowledge from CPT and the conversational behavior from fine-tuning. That two-stage pipeline is what separates a genuine domain expert from a model that just got instruction tuned on medical quanda. The result of that pipeline is a model that can reason like a domain expert and communicate like an assistant. Both properties matter, and neither stage alone gives you both. Domain adaptation checklist. 1. Before you run CPT, verify your data. 10 million to 100 million tokens of domain text, mixed with at least 50% general data, filtered for quality, and tokenized for causal language modeling. In your training configuration, confirm the learning rate is between 5e5 and 1e4. Epochs are set to 1 or less, and checkpoints are saving frequently. During training, run periodic general knowledge tests, not just at the end. If forgetting appears, stop and adjust. After training, validate that domain performance improved by more than 20% and general knowledge accuracy is still above 80%. Hit both thresholds and your model is ready for the fine-tuning stage. Key takeaways. 7 things to carry forward from this lesson. CPT teaches knowledge. Fine-tuning teaches behavior. Keep those roles distinct. Mix domain and general data at roughly 50/50ths to prevent forgetting. Use the learning rate between 5e5 and 1e4. Lower than fine-tuning. Much lower than original pre-training. 1 epoch is usually enough. Overtraining accelerates. The professional pipeline is always CPT first, then fine-tuning. Never skip the first stage for serious domain work. Test general knowledge throughout training, not just at the end. And the performance target is achievable. 20 to 40% improvement in domain-specific tasks is realistic with this approach on your hardware. What's next? You now know how to take a general model and make it genuinely knowledgeable in a specific domain. That's a capability most practitioners never develop. The next lesson builds on this foundation. Lesson 6.5 covers custom architectures, where you'll go beyond standard LoRa configurations and start shaping the model's structure itself. Additional resources. Vadiu EQ Wines. Additional resources. For deeper reading, the CPT section of the Llama 2 paper explains the original researchers' approach to domain adaptation. The Domain Adaptive Pre-Training paper is the academic foundation for the mixing strategies covered here. For the forgetting problem specifically, search for catastrophic forgetting in neural networks. It's a well-studied area with a rich literature. PubMed and the Stack are the data sources used in this lesson's examples, and both are freely accessible. Your model is now a domain expert. Time to customize the architecture. Here's the end-to-end flow visualized. You start with a general language model. Broad knowledge, no specialization. You feed it a domain corpus through the CPT process. and outcomes are domain-adapted model that understands the vocabulary, concepts, and reasoning patterns of your target field. From there, you have two paths. Deploy the domain model directly for tasks that only need knowledge retrieval, or run a task-specific fine-tuning path to shape its behavior for a particular application. That fine-tuned model becomes your production system. The important thing to internalize about this diagram is that CPT and fine-tuning are sequential, not interchangeable. Skipping CPT and going straight to fine-tuning on domain Q and pairs gives you a model that mimics domain language without actually understanding it. The CPT stage is what builds genuine comprehension. Data mixing ratios aren't one size fits all, and this comparison makes that concrete. For a medical domain model, a typical effective mix is 60% medical papers, 25% general web text, with the remainder split between Q pairs and code. The high domain proportion reflects the density of specialized terminology in medical literature. The model needs heavy exposure to absorb it. For legal domain adaptation, the distribution shifts: 40% legal documents, 25% Q pairs, 20% general web text, and 15% synthetic text. That synthetic component is deliberate. Legal language is formulaic enough that synthetic examples can meaningfully supplement. The key insight from both distributions is that neither is 100% domain text. General data is always present, always serving as the anchor that prevents forgetting. When you design your own mixing strategy, start with these as reference points and adjust based on your evaluation results. This graph makes the case for replay buffers more convincingly than any written explanation could. The x-axis is CPT training steps, the y-axis is benchmark score. The naive approach, training purely on domain data, shows domain scores improving but general scores degrading steadily. That's catastrophic forgetting happening in real time. The replay buffered approach, shown by the blue line, tells a different story. Domain benchmark scores climb significantly while general scores remain stable. The replay buffer is exactly what the data mixing strategy in this lesson implements, continuously interleaving general examples with domain examples, so the model never fully shifts its attention away from foundational knowledge. If your training curves start to resemble the naive pattern, the fix is straightforward. Increase the proportion of general data in your mix. Curriculum learning is an optional but powerful extension to the CPT approach. Rather than presenting all domain documents in random order, you sequence them by difficulty. Training begins with high-frequency, clearly written examples, the kind of text where domain terminology appears in obvious context. The model builds a foundation. Then you introduce medium difficulty domain-specific examples, followed by rare and complex cases that require genuine domain reasoning. Throughout this progression, the replay mechanism keeps injecting general knowledge examples alongside the new domain data. The result is a model that learned domain knowledge the way a human expert would. Foundations first, complexity later, with continuous reinforcement of general reasoning. This approach requires more upfront data curation, but it tends to produce more robust domain adaptation, particularly for fields with highly specialized edge case vocabulary. Two mixing strategies worth understanding clearly because the choice between them has real consequences. The aggressive strategy uses 80% domain data and 20% general. It maximizes domain immersion. But that 20% general buffer is thin enough that forgetting becomes a genuine risk, especially over multiple training epochs. The balanced strategy splits 40% domain, 40% general, and 20% diverse sources. That diverse 20% is valuable. It includes text types, code, dialogue, structured data that don't fit cleanly into either the domain or general categories but contribute to overall language robustness. For most projects, the balanced strategy is the right default. The aggressive strategy is appropriate when you have strong evaluation infrastructure to catch forgetting early and the willingness to retrain if it occurs. This perplexity curve is one of the most useful diagnostic tools you have during CPT. Perplexity measures how surprised the model is by the next token. Lower perplexity means better prediction, which means better domain understanding. The blue curve, domain perplexity, drops sharply in the early training steps, that fast learning phase marked on the left, then continues declining more gradually. That's exactly what you want to see. The orange dashed line, general perplexity, is the one to watch carefully. As long as it stays flat or trends slightly downward, your forgetting prevention is working. If it starts climbing while domain perplexity is still falling, that's the forgetting signal. Time to adjust your learning rate or increase the general data proportion. Check both curves together, not in isolation. A model with excellent domain perplexity and rising general perplexity is not a success. The CPT evaluation suite gives you 6 distinct signals, each measuring something the others don't. Domain perplexity tells you how fluent the model has become in domain text. General perplexity is your forgetting detector. Watch it for any upward movement. The domain task benchmark measures practical accuracy on domain-specific questions, which is closer to real-world performance than perplexity alone. The general benchmark, typically MMLU, checks whether foundational knowledge across science, history, and reasoning is still intact. The hallucination rate is particularly important for high-stakes domains like medicine and law. A model that sounds confident while generating incorrect information is actively dangerous. Finally, the instruction follow metric measures whether the model still responds well to user directives after CPT, since continued pre-training can sometimes degrade instruction following behavior. Run all 6 after every. Together they give you a complete picture of what the model gained, what it retained, and where it needs work.